Hi, I'm Francis, and today I'll be talking about graph convolutional networks for unstructured flow field data. So the motivation for this work is that unstructured data is frequently produced during many fluid mechanics applications, both simulation and experiment. So for simulations, you might use it as a way to efficiently parameterize curved surfaces and by using unstructured mesh. And in experiments, you might use sparse measurements in your domain to characterize a flow. And if you were to apply traditional machine learning methods to it, you would run into an issue in that the traditional machine learning methods require spatially structured data where each feature between samples has the same index because the specific index within a sample has some inherent meaning to it. For instance, a specific pixel in a sample versus pixel in a different sample has some information about what is different between those two samples. In addition, each sample must also have the same number of features. So if you're trading on two different images and let's say a convolutional neural network, each sample must have the same number of pixels because that's predetermined in your neural network implementation. However, this is not always feasible for unstructured data applications because in these applications, you might have, for instance, on this plot here, cases where you have features, a different number of features for each sample, or a situation in which there's no straightforward way to assign an order to these features. This is where we introduce a network representation for performing inference on these cases. So the case study that we'll be studying in this work is the body force prediction of laminar flow over 2D airfoils. So essentially we have a 2D airfoil immersed in a uniform stream and predicting based on the velocity field that results from this simulation, the body force or the drag force acting on this airfoil. And in order to generate this velocity field and pressure fields, we're using the Phoenix simulator package in Python to produce these simulations, and boundary conditions being slip conditions on the top and bottom walls of this domain. And in addition, we have pressure at the outlet is equal to pressure of the atmosphere. And we're solving just the straightforward irrepressible neighborhood equations and also implementing mass conservation as well. And to generate different airfoils and different orientations and different shapes, we're using the UIUC airfoil database. So the UIUC airfoil database contains 1600 airfoil coordinates. And after removing any airfoils that cannot be straightforwardly inserted into a CFD solver, we're left about 1550 airfoil geometries. So we create two data sets based on these airfoils. We have the first data set where we take every single airfoil and then generate the velocity fields from that airfoil. And we have a second data set where we sample 500 of these airfoil geometries, and then from these geometries, we take each geometry and rotate it by some specified angle of attack, anywhere from -10 degrees to +10 degrees, incremented by 1 degree increments. So we have 21 different angles of attack. And for each of these samples in both data sets, each airfoil is normalized to have a unit chord length, so there's no influence of the length of the airfoil on the resulting drag value. It's just based strictly on the cross-section shape. And we create an unstructured mesh around this airfoil to parameterize the velocity field using the open source package Gmesh. On the right-hand side here, I have a plot of the non-dimensionalized drag versus the non-dimensionalized thickness to give an idea of what airfoils are being used in this data set. Next is the graph encoding of field data. So in order to represent this velocity field in a graph representation, we define an undirected graph G with V vertices and E edges. So essentially, our mesh nodes are converted to V graph vertices. Our node connections, which is the connection between individual nodes in our mesh, are the E edges of the graph. And the components of velocity and Vx and Vy in both X and Y directions act as the node features that are parameterized by this graph. So after this graph encoding process, we're left with a matrix V by 2, which encodes the velocity information at each vertex for a given sample, as well as an adjacency matrix, which denotes the connectivity of the nodes inside the mesh. So for any given pair of nodes, I, J, in this adjacency matrix, in
Entry ij in this matrix is set to 1 if they're connected and 0 if there's no connection between these two nodes. This gives us kind of an idea of how the structure of the graph is overlaid. And in order to perform learning, we use the GraphSage framework, which was developed by Hamilton et al. In the 2017 paper, Inductive Representation Learning on Large Graphs. And this provides a low-dimensional embedding of nodes, which improves computational efficiency, especially in large graphs, which are common in fluid mechanics applications. So the reason why we're able to use a different number of features for each sample is that this is an inductive method as opposed to transductive method. So it operates on the individual nodes. And the general framework is that for any given node, we sample nodes in this neighborhood. We use an aggregation function that performs a weighted average, where these weights are learned based on the data to concatenate the information into a single, that gets the node. And based on this, and now this node has an embedding of all the information stored in this neighborhood around it, according to this pseudocode here. So if we were to apply this to our fluid mechanics problem, we would have our node features, which is the UX and UI defined on each node. And then we perform a weighted average first of all the nodes surrounding it in its immediate regions that are one edge away from the node. And in addition to that, we also perform a weighted average on all the nodes that are 2 edges away. All these nodes in teal or light green, as you can see here. So this means that this node in red now has information from both 1 neighborhood away and 2 neighborhoods away, which essentially implements convolution on a network representation. So the general architecture is as follows: we input into the model the node feature matrix, and you can see a matrix as input, and we perform graph convolution to create this matrix of V by 256, where V is the number of vertices in any given graph, and also implement top K pooling, which is another technique to improve the performance of our network by implementing something that's analogous to dropout, where you have a learned score assigned to each vertex, and the top K vertices based on the learned score are taken and propagated to the next layer in our model. And this reduces the computational expense of running this model, and it also improves accuracy by implementing an analog to dropout as we would find in a traditional multi-layer perceptron network. And on the output of after each graph convolution and top K pooling layer, we perform max pooling and mean pooling to extract the mean and max of our graph convolve layer. And we feed these many max pooled layers, connect these together, and then we feed them to a simple MLP to generate the final drag force prediction. And this skip connection is important, where it connects the second and fourth layers together, because this essentially reinforces information from the second layer that might be lost after successful convolutions. So this improves performance by putting the skip connection layer. So upon applying this to our data set, to both data sets, we see good accuracy and good agreement between predicted drag force and actual drag force. So we plot the graph of the predicted drag force on the y-axis, actual drag force on the x-axis, and the slope is very close to 1, and the R-squared value is also very close to 1, which indicates that we are achieving great accuracy on both data sets, both the training set and the validation set. And in order to have a good comparison to other machine learning models, we select 3 different commonly used machine learning models in similar situations, such as GB, which is gradient boosting, gradient boosted random forests. We have MLP, which is multi-layer perceptron, and a CNN, which is a convolutional neural network. And to generate a feature matrix that's interpretable by these methods, we construct a distance metric based on the distance of any given vertex to the center of the airfoil. We sort the vertices based on that distance metric, and then we select the top n vertices, and in this case n equals 1000, to generate a feature matrix. And this makes it so that
we have the same number of features for each sample, and additionally, the position of each feature within the sample has some inherent information contained within the index. But upon comparing these three different methods to GCNN, we find that the GCNN is easily able to outperform them with R-squared very close to 1 on both data sets with training and testing. And this is done by close cross-validation, which gives us estimated standard deviation of the accuracy of our model. Next, to examine what the graph convolution methods are able to expose, we perform visible component analysis on our data, specifically on the output of our neural network after successive graph convolution calculate pooling layers have been applied, and mean-max pooling has also been applied as well. So visible component analysis, this is a quick refresher. This performs a singular value decomposition on our feature matrix, and based on the singular values, it's up to the top L singular value components and their corresponding vectors as describing in the variance of the data. So in this case, L equals 2, which provides us with a nice way to graph our data and see how well it separates. So after performing visible component analysis on our data, we see that it's cleanly separated into these 2 dimensions here. So I have this graph from before, the drag versus thickness for dataset 1. So we can see that in the actual dataset itself, drag is pretty strongly correlated with thickness, and we can see it's reflected in the visible component graphs here. So without any spatial information provided to the graph convolutional neural network, there's no coordinates. The only information that's provided is just the velocity fields. We can still see the clear separation of the geometry of the airfoils in the principal component space. So in principal component 1, as you go from left to right, you have essentially a measure of the thickness of the airfoil from this extreme end to this extreme end. And in principal component 2, as you go from top to bottom, you essentially have a measure of the cross-sectional shape of the airfoil. In essence, how quickly it tapers for any given airfoil from this sample to this sample. So it's interesting that based on velocity field itself, without any special information provided to the network, graph convolution is able to recover this innate geometrical structure to the data that was not provided to it a priori. So in conclusion, we have presented a graph-based approach for performing inference on unstructured field information. And we still have the same advantages as you would see in a convolutional neural network, where we have automatic feature detection as well as parameter sharing. But in this case, it's applied on a network basis. And this model can achieve high accuracy when regressing for the body forces or performing graph level regression in general on fluid mechanics problems. So some interesting future applications of this work would be to extend the use of the GCNN framework to more complex inference problems, such as laminar flow around different shapes, where there might be other complex flow phenomena happening. So for instance, in cylinder flow, you might have vortex shedding and so on and so forth, as well as performing node level regression, where you're instead of regressing for a value for the entire graph, you're regressing for values on a specific node to recreate localized features of the field, like a pressure gradient or a velocity formation. And that's all for today. Thank you so much for listening to my presentation. Thank you.